Hello, my name is Camille Skavinsky and I'll be explaining to you guys how drag forces are affected on various bodies. Here we have three different angles of attack for an airfoil. As you can see, the first one and third one are completely different. The second one is kind of in between of both. Basically, drag is basically the disturbance of the force of air or any type of fluid, and it becomes disturbed and it causes kind of like a circulation of a whirlpool effect, or just becomes all jagged just based on how the flow is being forced to go in a different direction. The third one, as you can see, is really bad compared to the first, just based on how the angle is, and the air is being forced more towards the bottom. But at the top, it becomes disturbed and it starts having a little type of a whirlpool effect. Here at the bottom, as you can see, this is a good example of the whirlpool effect, where the air is kind of forced to spin around just based on how it's being disturbed or guided by the angle of attack. And then in the experiment, we did a circular prism, and what happened was here the air is being guided around both edges, and it becomes symmetrical just based on how the shape is, and it causes a whirlpool effect as well because of how the air is being guided around, forced to the sides, but since in the middle there's no way or direction for it to guide it, it starts spinning in a circle. Now, we analyze drag forces on a bunch of objects. Usually it's cars or anything that has to go or is in motion, just to see how efficient it is. Obviously a box is way worse than this car. The box, it stops the air at that exact point, and then it causes it to move around, or just stop it and then guide it around it just because of the shape of it, as you can see by the orange, and the orange here by the car. The car is more aerodynamic, so it has less drag forces. Drag forces is where it stops and it causes a resistance to the flow itself. And then in lab report number 4, the drag force of the square cylinder at 0 degrees was 0.9 newtons, and then the drag force at 45 degrees was 0.77 newtons. The drag force is highest at 0 degrees, and then the angle where it's highest for the drag coefficient will be 0 degrees as well. And this is reasonable because the air will be acting on the square cylinder higher than based on the face that faces more resistance. You can see, like in the car kind of, the resistance is higher when it's flat, but if it was at an angle, it'd be less, just like the car. And in lab report number 6, it depends on the locations of the pressure taps. As you rotate it, the pressure tap is turning away from the initial point of attack of the airflow, and the circular cylinder has a uniform shape. And the drag coefficient changes based on where the pressure tap is located. It flows smoothly around the cylinder, but compared to the square prism, the flow is kind of cut and stopped, and it's guided kind of like a knife, which creates a higher drag coefficient because it's being forced immediately and not kind of guided smoothly. And then for lab report number 6, by examining the pressure distribution on the airfoil, the angle where the airfoil has no lift will be at 26 degrees, and then the airfoil regains lift again at 11 degrees. And for question number 3 about the flagpole, the drag force was 268 newtons, and the bending moment will be at 1,228 Newton meters. And the Reynolds number for the pole is greater than what we experienced in the experiment, but it varies under many conditions, and it will always change based on how the parameters of the pole are and the conditions where it's at.